So, in other words, gravity accelerates all objects at the same rate. Why do I feel like this lesson is going over like a ton of bricks?
Well, these kids look more confused than a newborn hog in a funhouse. But don't take it too badly. Gravity is a heavy subject. Sometimes students' misconceptions can make it feel like an uphill battle. Remember when Justine revealed her ideas about the way things fall?
This one time, I tried to dunk confetti on my baby brother, who kind of crawled like a snail through mud. And it took forever for it to reach the ground, so I know that lighter things fall more slowly.
But I don't understand. I very clearly demonstrated that lighter and heavier objects fall at the same rate by dropping that tennis ball and basketball from the same height. What more proof do you need?
All kids come in with ideas about how and why things fall, ideas they picked up from books, from conversations, and from living life. A lot of those ideas contradict what you've shown them. Assuming that one demonstration proves a scientific point tends to brush students' lived experiences aside. After all, Justine is right about the fact that confetti falls slowly.
So what would you suggest?
That we call in the reserves. Wakey, wakey, eggs and bakey.
I was just having the most spectacular dream. I did an around the actual world.
Well, be sure to note it in your dream log. In the meantime, we need your help with gravity, Bert.
Then you came to the right play, Toy. Yo.
Yo.
So here's the story. If you're anywhere near other matter, you're affected by gravity. Trust me, I should know. So, unless we're in remote outer space, so far from anything that there's practically no gravity, we're experiencing it all the time. But that doesn't mean we always know how to talk about it. It's kind of like love in that way.
Yeah, sure.
Because most of us spend all our time on Earth, it's easy to get casual about the difference between mass and weight. But to really understand gravity, you'll need to be a bit more precise.
Who here has heard the word gravity before? Can anyone tell me what it means?
It makes things fall because the air is pushing them down.
Oh man, if I had a nickel for every time I've heard that one. Kids always draw on their personal experiences first, and all of their experience with gravity is within Earth's atmosphere, where there's air. Of course, it doesn't help that the astronauts in all their favorite movies and shows always talk about experiencing 0G or no gravity. So because there is air on Earth, they think that gravity must require air. Trust me, if there were no gravity in space, those astronauts wouldn't be safely orbiting the Earth.
Well, let me try to explain it in another way. Gravity is a force that all matter exerts on all other matter. It doesn't need air or any other medium, just two objects. But to really feel it, you need a whole lot of matter. That's why when we talk about gravity, we're usually talking about planets or stars. Now, what about weight? Justine?
Weight comes from a scale, like the one in our house my dad is always cursing at.
Well, the scale is definitely measuring weight, but where does the weight come from? The question is, what is the scale measuring?
My dad's love of stuffed crust pizza.
Maybe be a little less specific.
How big you are.
And how does it do that?
It feels how heavy you are.
That's right, Justine. A scale measures you pressing down on it, and you press down on it because gravity pulls the matter in you towards the matter of the Earth beneath the scale. Weight is determined by gravity. Mass means how much matter an object is made of. It's an intrinsic characteristic. Take these two apples. This one has a greater mass. It's made up of more matter than the smaller one. The weight of these apples changes if gravity does, but their mass stays the same no matter where they go. So when I said earlier that you would weigh less on the moon, that means there would be less force pulling you towards the moon.
Maybe my dad should try living on the moon.
I don't think he'd like that.
You're probably right. The commute alone.
I like where this is going. A lot of folks don't get the difference between mass and weight. because we're only used to experiencing one gravitational field, the Earth's. It's easy to get lazy and use weight and mass interchangeably. Boy, does that get my goat.
Exactly. Well, except for that thing about getting a goat. That was a little freaky, my man. Remember, your students aren't the first to be confused about gravity's effect on different objects. Scientists have grappled with these ideas for centuries. Take that brainiac Aristotle. He thought that heavier objects fell faster than lighter ones, and he was a legend among ancient Greeks, or as he would have called them, Greeks. Or take Galileo. A couple thousand years later, he theorized that free-falling objects fall at the same rate regardless of their weight. More recently, modern astronauts were able to compare a hammer and a feather falling on the moon, where there's almost no air and weaker gravity, and got the same result. We observed the same thing on Earth, where the gravity is much stronger, when NASA scientists tried it out in a giant airless vacuum chamber. Teaching the history of science and seeing how different ideas were tested until scientists arrived at a better understanding is a legit way to show students how to think about their own ideas.
Wait a minute. I know what you're saying is true, but if I have a really massive object, isn't the force going to be a lot stronger? Why won't that make it fall faster?
That's a great question. See, here on Earth, gravity speeds things up by 9.8 meters per second for every second that they're falling. Big or small, heavy or light, always. But don't forget inertia, the tendency of an object at rest to stay at rest. A more massive object has more inertia than a less massive object. That inertia is always in the same proportion to the force of gravity.
So the heavier object's resistance to changing its speed, in this case falling, cancels out the stronger pull of gravity, and the acceleration, like you said, is always the same.
You got it.
But what about Justine and the confetti? She wasn't wrong exactly. Confetti pieces do fall slowly. Her experience wasn't incorrect, but the way she applied it was. But I'm getting out of my depth here. Yo-yo?
Oh, sorry. I thought you meant yo-yo like, yo-yo, what up?
Why would I? Oh, never mind. Just help me out here, Albert.
The confetti wasn't falling slowly because it's light, it fell slowly because of air resistance. The difference is between real and ideal situations. On the chalkboard or in a vacuum chamber, we can just focus on the force of gravity for any pair of objects. But in most everyday situations, we are surrounded by air, and some objects are much more affected by air resistance than others.
Right, and that air pushes back against any object moving through it.
Oh yeah. It's a complicated relationship between an object's speed, how much area it has, and how rough or smooth it is. Kids see this all the time. They know that if you stick your hand out a moving car window, it's easier. That is, there's less air resistance if you make your hand into a blade than if you make it a sail.
That sounds like a fun starting point for a discussion about gravity and air resistance. I know every time I'm in the passenger seat, I do that hand wave thing, you know.
Whatever floats your boat, Teach.
I told you this gravity business was tricky, Isabella. But if we start by listening to students' ideas and then have them engage in a wide range of both everyday scenarios, like dropping objects off a roof, as well as ideal ones like watching a demonstration in a vacuum chamber, we can use their initial observations to help them understand, rather than leaving them confused.
I think I got it now. Thanks, you two.
You are most definitely on a roll. Now, if you'll excuse me, there's a Swedish fish with my name on it.
That belongs to one of my students.
Have you seen what sugar does to the kids in your classroom?
Eat the fish. To discover more about how kids learn science and the types of misconceptions they might have, visit us online at scienceeducation.si.edu/good thinking.